right, good morning everybody. Hello, hello. Today we are going on a new and wonderful adventure into the next chapter where we will spend the briefest amount of time, dabble a little bit, play around with the good stuff, and then move on to the next thing. We are officially in the skipping stone, hopscotch kind of phase of the course, where even though we've got this wonderful textbook that gives us a great outline of course content and subject matter and lines up and this thing into that thing, and we're not going to dive into everything. Okay, we're only doing half of chapter 5. We're going to do a bit of chapter 6. We're going to do a bit of chapter, and then we do like jump to 10, I think is the next one, right? So we're bouncing around all over the place, just grabbing the highlights, just the main bits, because remember, this year being as wonky as it is, I am trying to focus in on, okay, there's all this good stuff that they say is pre-calc, but only some of it is actually useful for calculus. There's a lot of other ancillary bits and great mathematics. Don't get me wrong, it's good stuff, worth looking into, but it's not going to help directly with calculus itself next year. Okay, so that's why I'm leaving a lot of those things behind. Okay, and we got a bunch of people: Ivan, Lewis, Manny, Mariana, and okay, that's all of them. Excellent. Everyone is now here. So, before we get into today's topic, we had the test on Monday, and overall that went very well. I personally really like that test format. I think quizzes, with some of the extra features now that it has, can work rather well and better than Google Forms. If you have any feedback on that, let me know. In fact, I might just go ahead and put up a straw poll after asking which you prefer, the quizzes format or the Google Forms format. But the quizzes lets us do a couple retakes right then and there. And I think that's the main benefit. Anyways, now that that's out of the way, we're not quite out of the trigonometric woods yet. So ideally, you would have read and taken notes on the next section. And this next section is, in a way, it's fairly simple as far as sections are concerned. Some of these sections in the book, they like to throw lots of different aspects and pieces at you. This one is fairly straightforward. But the process itself can get messy. So let's work our way through verifying trig identities. All right? Make yourself comfortable. I'm going to try to do as many examples as I can. I really, this is where the Zoom format is really going to interfere, okay? Because I would like for you to work along with me, go through the examples yourself, okay? That's the best way to make use of them. So I'm going to move slowly through them. I'm going to give you a chance to try the next step yourself, and then I'll go a step. And give you a moment to try the next step yourself, and then I'll do a step, okay? Unfortunately, I can't have you like type it in and give me answers as to how you're going every step of the way. But please, please, please follow along as we're doing this. All right. First, a number of questions. Verifying trigonometric identities. Okay, we know what the trig part means, right? Trigonometry, the triangles, the unit circle, sine and cosine. Okay, it's all that stuff. But what the heck is an identity? I mean, I know what like my identity is. It's who I am as a person. Like, is this sine and cosine's driver's license? No. An identity is a true statement. Okay. In fact, it is always true. And it's usually about at least, so greater than or equal to 2 functions typically functions are involved. Sometimes you might have constants in there. Okay? It's also a statement of equality. Okay? And that's probably the most important aspect. An identity is an equality statement that says this thing right here is always exactly the same as this other one here. Okay? This function, this convoluted sine squared plus cosine minus the tangent divided by the secant, whatever they've done to it, is equal to this function over here. Why is that useful? Right, that's probably your next question. Well, why the heck would you want to do that? Because, I should probably do this in a different color. Let's use a nice dark purple. Okay. It lets us change the look of functions, usually to be easier to work with. Okay? The point of these trig identities is to take what you will encounter in calculus, find the integral of this gigantic nasty thing. You're like, oh my gosh, and you start freaking out. And they go, oh wait, trig identities. I can just turn this chunk into that, and turn this chunk into that. And now it's just 1 plus 2. Oh, the whole thing, it like reduces to 3, right? All of a sudden, this large, convoluted, right, complicated thing simplifies. Right? Usually we're going to try to make things easier to work with. The identity is what lets us substitute one function for the other. So do you need to memorize these things? Yes, I'm going to agree with the book on this. Yes, to an extent. And I'll show you exactly which ones to focus on. It's not that bad, okay? Right here, the fundamental trigonometric identities, okay? Right here at the beginning of the section, page 622. Some of these, most of them, you probably already know. The reciprocal identities, right? We've defined cosecant as 1 over sine. Okay? So you should be able to, with a second of thought, be able to be like, oh yeah, well that works the other way. If I take 1 over cosecant, I'm back to sine. Okay? So these ones we kind of already know. You should already be committing those to memory. The quotient identities, again, tangent, we usually define it as sine over cosine. Cotangent is defined as cosine over sine. Right? These you should basically already know. These guys down here are the new ones, right? Pythagorean identities, of course, coming from Pythagorean theorem, a squared plus b squared equals c squared. I think we kind of talked about this beforehand. Okay? So a squared plus b squared equals c squared. On the unit circle, draw your triangle. Our unit circle, c squared, is always 1, right? C is 1. Our a is the x value, our b is the y value. X value comes from cosine, y value comes from sine. Okay, so there, real quick, is the, I wanted to erase this stuff. There we go. Apparently it likes highlights first. But I want that highlighted. All right? So Pythagorean identities, super useful, especially because they involve stuff squared, okay? This is the only versions that have stuff squared. That can be incredibly useful there. And then the even odd identities, look at these guys. These lets us swap back and forth. Sine of negative x instead makes it negative sine of x. And that just is symmetry, okay? It's looking at the graph and saying, hey, is this symmetrical about the x-axis, about the y-axis, about the y-axis, about the x-axis? Make sure my gestures are matching up to what I'm saying. So yes, do you have to memorize the things in this box? It's going to make your life so much easier, okay? These are the basics. Everything else is built upon these things. the better you have these memorized, it's like having your multiplication table memorized, okay? It allows you to do stuff faster. So yes, 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 yes. Get these memorized. Make some flashcards. All right. Final question. What is verifying, and why are we doing that part? If these are so useful to swap out in calculus and switch one for the other, why are we like verifying? This is already, right, here's an example. You're already telling me that this stuff is equal to that. Well, can't I just like put this on a giant list of trig identities and say, take this and simplify it to that thing? Maybe, like, do you want to memorize just the basics, that table, or do you want to try to memorize all possible trig identities, right? Every possible combination. It's endless, okay? There's way too many to memorize. There's also way too many to have on a convenient table. You're always going to run into something different, okay? So what is verifying is practice. Why do it? Because you need the skill of making things look better. Okay? You want to practice turning larger, convoluted seeming trig functions into simpler trig functions. Right? So the verification process is one way of doing that. Instead of just giving you, like, can you imagine? Instead, we didn't have this, we didn't have this. We just said, simplify that. You would get to the same place. Your final answer would be the same thing. It would be, oh, this simplifies to 2 secant x. But you have no idea where you're going. You don't, I'm like, I could try this thing, I could try that. You don't know if you're going to get a simplified answer yet or not. Okay? So the verification process is so much kinder. Okay? Keep that in mind when you're doing some of these on your homework. You're like, oh, this is a terrible experience. Why? Like, well, it could be worse. This is so much better because it gives you the goal. You know where you're heading, and you can stop and pause. If you ever get lost, remind yourself, hey, wait, I'm trying to get to secant x. What do I know about secant x? You can expand from there. In general, the rule of thumb is to, let me go back to purple. Wait, one. You're going to work from more complex to less, and 2, stick to one side if you can. These are general rules. It's not hard and fast rules. I've seen some texts, they introduce verifying trig identity, and they say some stupid thing like, you have to only do things to one side. You are not allowed to interfere with the other side at all. That's bogus, okay? It's complete malarkey. It is not an actual mathematical rule. There's no reason your proof cannot involve algebraic operations on both sides of the equation, okay? But it will help you to try to stick to that one side and always work on, I'm trying to make this side look like the other. But if this is your end goal, problem-solving strategies apply here. If you're not sure what to do, sometimes it's easier to work backwards. Be like, ooh, 2 secant x. Well, what do I know about secant, right? Secant, this could be 2 over cosine x, right? Maybe thinking that way, oh, maybe I could get these in terms of something over cosine x, right? So maybe sometimes doing a couple steps on the other side just to see where you could go with it can be helpful. All right, any questions on the general idea, the full scope, the overall strategy before we actually start these examples? I think I'm going to put this somewhere. Here, we'll just put it off to the side here. General strategies. Okay. All right, seeing no questions, then let us begin. First, pick a color. Let's go with orange. Why not? Just do something different. Rewrite cosine squared x plus cotangent squared x plus sine squared x in terms of cosecant x. Okay, so this is kind of like a verify. We want to turn this into cosecant x or cosecant squared x or 2 cosecant x, right? Something like that. What do we have to work with? I see things are squared. Okay, flags going off in my mind. First step, things squared. I need to involve the Pythagorean identities. What do we have squared? I've got cosine, cotangent, and sine. So let's look, see what jumps out to you. Here's sine and cosine together. Here's cotangent and cosecant. Ooh, hey, I wanted to get to cosecant. I bet I'm going to need some of these things. So I'm going to say go from more complicated to less complicated. Sine plus the cosine makes 1, so let's make that happen. All right, first we're going to take this plus this. So now we have 1 plus what's left. I still have cotangent squared x, right? And cotangent squared x plus 1 equals cosecant squared x. Hey, look at that. We just bring in that identity. This reduces to, pencil, cosecant squared x in terms of cosecant, and that's my answer. This whole thing is just this. Look at that, right? So, again, if this was something in calculus, instead of having to deal with 3 parts, right, 3 functions added together, you'd be like, oh, it's actually just 1 function, right? So much simpler now. Okay, next one. I was teasing you with this earlier. Now we're going to verify this guy, right? 1 over secant x plus tan x plus 1 over secant x minus tan x. Ooh, okay. Equals 2 secant x. Nuts. What do we have to work with? I've got my reciprocals there. 1 over secant, but it's secant plus tangent and secant minus tangent. It's like, I can't just use these directly. Okay? So I'm going to have to use some other techniques here, right? Not just trig. Remember, the rest of algebra still applies. These are rational expressions, right? Ratio of 1 to secant x plus tangent x, right? Giant fractions, ratio. I'm trying to add fractions here that do not have a common denominator. And what I get is something that doesn't look like a fraction, right? So this is like, somehow is 1/2 plus 2/4. And I'm actually getting a whole number there. See what's happening? Ah, so I need a common denominator. Okay, let's make that happen. What is the least common multiple of secant plus tangent and secant minus tangent? I don't think there is a simpler one other than just multiply by each other. So here's what I'm going to do. I'm going to duplicate that, and we're going to take this guy, and we're going to multiply by the other denominator. You get secant x minus tan x over secant x minus tan x. And this one multiplies by secant x plus tan x over secant x plus tangent x, right? Now they will have the same denominator. That denominator will be secant x minus tangent x times secant x plus tangent x. We'll simplify it in a moment. But notice what happens up top. This is multiplied by 1, so it is secant x minus tangent x plus secant x plus tan x. Okay. I see some simplifying. I've got minus tan and plus tan, so those reduce. So in the numerator, notice I just have secant plus secant. That is 2 secant x. Hey, wait a minute. That's what I'm trying to look for. Is it possible that the denominator down here is going to be just 1? That would be ideal. Can I verify that? Right? That's the trick. You don't just go, ooh, it'd be really convenient if it was just 1. That's the answer. Right? Because what if somebody pulled a sneaky on you? What if somebody gave you a verify this thing, but it's actually wrong? Okay? And you could prove that no, this is not possible because I can get to 2 secant x divided by 2. And they're like, look, it simplifies. There's no way to turn it just magically into multiply by 2. You can't do that. So we got to make sure this denominator is actually 1 and not 2 or 3 or anything else. All right. So let's, we got to distribute that. Okay. Secant times secant. We have secant squared x plus secant tangent minus tangent secant plus tangent squared. And secant tangent is the same as tangent secant, so those reduce. Right? If you remember your special products of factoring, you would have recognized that that is not plus. This is a minus tan. Okay? Okay, that this should have given us a difference of squares. Secant squared minus tangent squared. Now I have things squared. Let's check in with our Pythagorean identities. Is there one that involves secant and tangent? Ooh, look, tangent and secant. Okay, 1 plus tangent squared equals secant. Well, what if we did this? Subtract tan squared from both sides. Now I'll have secant squared minus tangent squared. That's exactly what I have in the denominator. What's on the other side of this identity? 1. So we can verify by means of this Pythagorean identity that yes, this denominator will equal 1, and so I will get 2 secant x. Verified. All right. So here comes the audience participation portion of the show. Number 3, verify that sine x equals negative cosine x times tangent of negative x. Okay, what's the side we're going to deal with, right? This side is simpler, this side is more complex. So in general, let's try to see if we can simplify this to make it look like that. So what are we first going to do? What are we looking for? See if you can predict a first step there. I'm looking at these and I'm saying, hey, you've got these negative signs here. And I know cosine and tangent and sine. I'm thinking ahead. How could I get cosine and tangent to combine to make sine? And what do I do about these negatives? Let's see if we can handle something about the negatives. What is tangent of negative x? Right? That's the real doozy here, because I can't combine this with anything as long as the arguments are different. Okay? Notice all of our identities, it's always plain old x in everything here, except for these. Oh, even odd. Tangent of negative x is the same as negative tan x. That's going to be the first thing we need to change. So this is negative cosine x times negative tangent x. Hey, negative times a negative is a positive. Look at that. Negatives no longer a problem, and now we just have cos times tan. How can we say that turns into sine? Take a moment, see if you can predict how that's going to work. How can cos times tan turn into sine? No, that's not going to help. No. Nothing is squared. Took care of the negative signs. Is your eye being drawn to this? The quotient identity of tangent. Tangent is sine over cosine. All right? When in doubt, rewrite things in terms of sine and cosine. Okay? In fact, I'm going to add that to my general strategy here. Right? Rewrite everything in terms of sine and cosine. That can be a great help. If you're not sure where else to go, you've got 6 different trigonometric functions. But thanks to those identities, any one of them can be rewritten back into terms of sine and cosine. It all comes down to just 2. And if you only have to deal with the 2 of them, usually things become a lot clearer of where you can go next. So let's keep going here. Instead of tangent, I'm going to have cosine times tangent is sine over cosine. Aha! Look at that. Cosine on the top and the bottom, they cancel out, and we have just sine x. Ta-da! Sine x equals sine x. Verified. Questions so far? No? All right, let's do one more. Yep, this is the last one. Verify. Oh, gosh. Ooh, that looks messy. That's tricksy. Look at this. It's like almost the same thing. 1 minus sine over 1 plus sine. And then minus 1 plus sine over 1 minus sine. Oh, jeez. They do this to us all the time. Why? Right now, the why is practice. Because in the future in calculus, you will encounter these things that you need to do calculus things to. And you would rather do calculus things to this instead of that. Why are we doing calculus to these kinds of things in the first place, Mr. Apple? Well, because you do your fancy, top-tier physics and chemistry experiments, and you end up with these funky kind of results, okay? All right. Real-world data is going to produce these types of functions, and so you're just going to have to deal with it, okay? So what do we do with this? Well, first and foremost, we've got rationals again, okay? So we can always get these into the common denominator, right? So how are we going to do that exactly? Have a comment. I think we're going to have to do the old multiply both of them by, duplicate of the same thing. So I'm too lazy to rewrite all of that. Although I can at least change it to blue, make it look like I rewrote it. Ha ha ha. And so on this side, oops, we have 1 plus sign denominator, so let's multiply by 1 minus sign over 1 minus sign. And over here, multiply by 1 plus sign over 1 plus sign. See what that does for us. So over here, we've got 1 minus sign times 1 minus sign. Well, that's convenient. Okay. And this is 1 minus sign times 1 plus sign, which is what we're going to have down here. So let's figure out that denominator first. I like finding out that common one. So 1 times 1 is 1, and then we have 1 plus sign, and then a minus sign, so those cancel out, and so it's just a minus sign squared x, right? Difference of squares, special product factoring. Okay? How about up top? We're going to have 1 minus 2 sine x plus sine squared x. And over here, we have 1 plus 2 sine x plus sine x squared, right? But there's a big fat minus in between them, so subtract all of that, and I'm just going to go ahead and distribute that negative. Say this is minus and this is minus. Okay, there is rational function dealt with, or addition and subtraction of rational functions dealt with. Anyone see the next step? See some things that simplify, combine. Yeah, after this, we've got some simplifying and combining like terms. Okay, I see some plus sign squared and some minus sign squared. I see 1 minus 1. Those go away, and so all we're left with is minus 2 sine, and 2 sine makes minus 4 sine x. All over 1 minus sine squared x. Ooh, it's getting close. Look at that. I've got minus 4. Look at that. I've got my negative 4. That's good. Now I need tangent and secant. How the heck am I going to get tangent and secant? Take a moment, predict, what do you think is going to be the next step here? Or a next step. There's not just one right way to go about this. Sometimes you can do some different steps in different orders. I'll tell you what I'm looking at. I'm looking at this sine squared. Right, it's the only thing left as squared. This is now much simpler than it was before, for sure. But sine squared. What can we do with that sine squared? 1 minus sine squared. Well, sine squared is an indication of a Pythagorean identity, and here's sine squared. But that's positive sine squared. But notice, if we subtract sine squared from both sides, I get 1 minus sine squared. That's what I have. That's what I want. What's left over here? These reduce, and I get just cosine squared x. Oh. So this is negative 4 sine x over cosine squared x. Aha, Pythagorean identity for the win. We're so close. We're so close now. What do you think we're going to do next? In fact, I'll make it easier for you. The next half a step, as it were, I'm going to spread out those cosines. See if we can deal with them independently. And a reminder of where we're going. Negative 4 times tangent x times secant x. Do you see it? Yeah, we're practically there, right? Each of those cosines is going to play a role in creating one of these, right? One cosine is going to combine with the sine. Sine over cosine is tangent, right? Light purple, right? Sine over cosine makes tangent. And this cosine x, pretend there's an invisible 1 there, right? 1 over cosine. Reminder of your reciprocal identities. 1 over cosine is secant. So that makes secant. This is negative 4 tangent x secant x. Done. Pretty sweet, huh? Okay, final call for questions. No? All right, we've got 7 minutes remaining. Take a look at tonight's assignment, give it an overview, read through all the problems, get a feel for it. Ask me any questions if anything seems confusing this time, and maybe get started. 5 minutes, that's enough time to finish 1 or 2 of them, I would think. You should be going faster than I am, because you don't have to stop and explain it out loud every time, right? Just do. And I will leave you to it. No class or office hours tomorrow because of the vaccine event. And do we have this Friday? We do not have this Friday. All right. Yeah, you work Friday, we're off Monday, you work Tuesday. I will not see you again until Wednesday. Oh my goodness, so long. But I gave you the option, the polls came in, it was close. Most of you decided, yeah, we would rather have the homework due Friday so you don't have to worry about it over the long weekend. So that is the expectation for everybody. If that's not feasible, you're like, Mr. Apple, something else is coming up, I really could use that extra weekend, shoot me an email, let me know, I'm happy to give you the extra time. But the due date for this homework, tonight's homework, plus the exercises of Monday, if you didn't get those done, get all that done by Friday. And then the only thing you have to do over the weekend is just read and take notes for the next section, okay? With that, I will leave you to it. We'll stop the stream here.